Everything looks green. The service responds, latency is normal, no HTTP errors. Monitoring is calm. Yet the golden set suddenly drops from near-perfect accuracy to 0. The model confidently returns wrong answers and ordinary metrics miss it. I inject an unknown incident with a fixed seed and deliberately do not reveal the fault to the agent. It gets one goal: find the cause, prove it with evidence, prepare a fix, and change nothing without approval. Watch what happens. The agent collects telemetry, inspects the latest release, and compares the model inputs. Its first hypothesis that the model weights regressed turns out wrong and it honestly drops it. Then it finds the real cause. The input color channels are swapped. It prepares a patch, runs 2 candidates in a sandbox, rejects the slow one, validates the fast one on quality and latency, and requests a Canary rollout. Minutes later, quality is restored, tests pass, and health stayed 200 the whole time. Today we build exactly this system. Not a chatbot, but a verifiable investigation and recovery loop where every step is backed by evidence. There is no magic here and no swarm of chatting agents. There is one incident commander, a bounded set of tools, and 3 parallel evidence collectors: telemetry, code, and model. The commander keeps a hypothesis board and at each step picks not any experiment but the discriminating one, the test that best separates one hypothesis from another. If the data contradicts expectations, it changes the plan rather than bending facts to a convenient conclusion. Then comes the safety loop. Any change first goes through a sandbox that checks both quality and latency. Then explicit human approval is required. And only then a Canary rollout that gradually raises the traffic share. This discipline, not model size, is what turns a bag of prompts into a reliable agent. Remember the chain: goal, evidence, hypothesis, experiment, gates, approval, Canary, verification. Let's set up the lab. At its center is a training computer vision service that classifies colored shapes. It has a golden set, pre-labeled images on which we measure real quality. That matters more than a 200 response code, because a service can answer successfully while being wrong in substance. First, we reset the lab to a clean state and take a baseline 100% accuracy. Then we run the fault injector with a fixed seed. It is deterministic but unknown to the agent. The true cause is written to a separate secret file the agent is forbidden to read. A second probe shows 0 accuracy at the same green health. Notice both commands and their output in the terminal. This gap between health and quality is exactly the silent incident most monitoring simply won't catch. Let's look at the metrics through an on-call engineer's eyes. The green line is service health. It stays at the top the whole time. The blue line is golden set accuracy, and that is what collapses. The yellow line is our quality threshold, the service level objective. Accuracy no lower than 90% and P95 latency no higher than 120 milliseconds. The key idea: health and quality are different things. A liveness check answers whether the service responds at all. Golden accuracy answers whether it responds correctly. A good incident loop watches the second one. If we tracked only status codes and latency, this incident would stay invisible for hours. So the first thing the commander does is treat measurable golden quality, not the health dashboard, as the source of truth. Now we give the commander tools, but narrow and verifiable ones, not arbitrary system access. There are only a few. Telemetry returns fresh metrics. Release inspection shows how the current release differs from the baseline. The model fingerprint compares weight hashes. Input comparison looks at channel statistics. And run experiment executes a patch in the sandbox. Note the security boundary. The true cause lives in a secret file, and any attempt to read it is blocked in code. This is essential. The agent must reach the answer through evidence, not peek at it. In the terminal on the right you see each tool actually called and what it returns. Health 200, accuracy 0, weight hashes matching, while the channel statistics already hint at a swap. No secrets or keys in the logs, only tool names and safe results. This is the heart of the approach, the hypothesis board. The commander does not rush to fix things blindly. It states hypotheses, assigns confidence, and for each keeps the next experiment that will test it. The first hypothesis is almost always the obvious one. If quality dropped after a release, the model weights must have regressed. It sounds reasonable, but reasonable is not the same as correct. A good board is one where a hypothesis lives only until the first contradicting fact. We explicitly show both confirmed and rejected hypotheses. A rejected hypothesis is not a mistake. It is a normal and necessary step of investigation. The presence of a discarded hypothesis is what separates an honest agent from one that backfits an explanation to an answer it already knows. On the right you see the event stream: hypothesis, experiment, decision, with confidence and evidence at each step. Let's test the first hypothesis properly, not in words. If the model weights had regressed, the binary weights of the current release would differ from the baseline. So the discriminating experiment is simple. Compare the cryptographic fingerprints of the weights. The commander takes the hash of the current release weights and the hash of the baseline model. They match to the last byte. The conclusion is unambiguous. The model did not change, so it is not the cause. The weight regression hypothesis is rejected, and that is a valuable result, not a dead end. In one cheap step, we just ruled out a whole class of causes and narrowed the search. Notice how it works. First, a prediction of what we should see if the hypothesis holds, then a measurement, then an honest comparison. Had we believed the first hypothesis and started retraining the model, we would have lost hours and fixed nothing. Now, the real cause. The commander compares the model's input statistics, how the color channels look under baseline preprocessing versus now. We take the red-colored classes, where normally the red channel is strong and blue is weak. And we see a flip, where red used to be around 80, it is now around 30, and blue rose the opposite way. The red and blue channels swapped places. To a human it would look like scrambled colors, and for the model it completely breaks recognition. It calls a red or blue and vice versa. Confirmation comes from release inspection. In the new release, the channel swap flag turned on. On the left, the chart shows the flip clearly, and on the right is the exact preprocessing line where the swap happened. One line silently crashed quality to 0 without touching health or latency. The cause is found, but we must not fix it directly in production. We prepare 2 patches and run both in a sandbox, on a copy of the release without touching the live service. The first patch is slow. It also restores the correct colors, but adds a heavy pass on every frame. We check the gates. On quality it passes, accuracy is 100% again. But on latency it fails. P95 goes past 150 milliseconds, above our 120 threshold. So the patch is rejected despite the correct answer. This is an important point. Correct is not enough. The fix must fit the latency budget. The second patch is fast. It simply turns off the channel swap. Accuracy 100%, latency a fraction of a millisecond. Both gates green. That is the one we carry forward. On the right is the exact diff, on the left the result of both gates. The patch is ready and verified, yet the system still does not roll it out on its own. Here sits the approval layer. The commander shows the on-call engineer a short diff, exactly what changes, a single preprocessing line, and offers options: show the full diff, approve a 10% canary, or deny. Nothing reaches production without an explicit yes. The point is blast radius. The more power automation has to change the system, the more expensive its mistake. So we deliberately keep a human in the loop precisely at the boundary of an irreversible action. As soon as approval arrives, we move on, but now with a recorded decision: who approved and what exactly. Even a verified patch we roll out gradually, not to all traffic at once. This is a Canary rollout. First, the new release gets 10% of requests, and we immediately measure quality on them. All good, we widen to 25, then 50, then 100%, checking quality at each share. If accuracy dropped at any step, we would stop and roll back. And to make this more than theory, we run a rollback rehearsal right here. We deliberately deploy a knowingly bad canary, catch the accuracy drop, and roll back to the working release. Recovery is confirmed by measurement. The idea is simple. A rollout must be reversible and observable. We never change everything at once, blindly. We move in small steps, each of which can be undone. Let's put it all into one run and look at it whole. A user message reaches the commander. It sees health 200, quality 0. It runs the cause search with its tools, gets the result, discards the wrong weights hypothesis, confirms the channel swap, prepares and validates a patch, requests approval, and rolls the canary. The logs show, in order, every tool call and the final answer. Compare this with a plain chatbot. It would just return text. Our commander chose which tools were needed, in what order to apply them, and at each step relied on measurement, not a guess. This ability to build a plan on its own, verify it with facts, and act safely over several steps is what makes it an agent. And notice, through the whole incident health stayed green, so without quality monitoring we would never even have learned that something broke. Every incident should end with an artifact, not just a green dashboard. The commander generates a report. A good postmortem answers several questions at once. What happened in numbers, what the real cause was, what exactly was used to fix it, and what was rejected and why. Here we see the accuracy path 100, 0, 100, unchanged health 200, 1 rejected hypothesis, the identified channel swap cause, the accepted fast patch, and the rejected slow one due to latency. On the right is the exact fixed diff. This report is reproducible. It is built from the same trace as the whole video, so its numbers are real measurements, not a retelling. This kind of artifact is what turns a one-off firefight into knowledge that stays with the team. Let's sum up with principles that transfer to any real system. First, an incident can be silent, so watch quality, not just health. Second, give the agent narrow verifiable tools and block direct access to the answer. Make it prove things. Third, keep a hypothesis board and don't fear rejecting hypotheses. A rejected hypothesis is progress. Fourth, validate any fix in a sandbox on both quality and latency. Fifth, irreversible actions only through approval and a canary rollout with rollback. What this is not. It is not a finished production SRE platform, but a reproducible learning lab with a real model, a real incident, and real measurements. A live Claude run may choose a different experiment order, and the deterministic trace you saw is built from actual lab execution. The code and the lab are in the description. Build it, break it, and fix it yourself.